Today's burning question, what gave me this reaction? Oh! The answer is sure to spark your interest.
Oh, fireworks!
As we find out all about fire and try not to get burned. I'm Nick Uhas. Welcome to Oddly Satisfying Science. As a scientist, I'm on a singular mission to find the coolest experiments the world has to offer.
Wow!
And see how they can improve our everyday lives.
That looks like magic.
With the help of some expert friends, we'll discover the secrets of the universe, one awesome explosion at a time. Seriously, do not try this at home. It's safe to say that learning to control fire is one of the most important discoveries in the evolution of human society. For over 100,000 years, fire has played a major part in our social lives. Campfire, s'mores, anyone? But it's also played a role in the development of our civilization. From early metalworking to modern-day car engines. Today, we're taking a closer look at all the things fire does, from flying lanterns to survival hacks, even space travel. In our next 5 experiments, we're gonna do fun, freaky, and fascinating things with flames. Starting with what seems impossible, lighting metal on fire. Today, we're gonna see how that can happen with some steel wool, a 9-volt battery, and my very first guest. This is my good friend Kat. She's an electrical engineer and she worked at NASA. And I'm really glad that you're an electrical engineer because today's experiment is all about electricity.
As you know, I absolutely love electricity, I love circuits, and I love igniting things with circuits.
Love it.
So basically what's going to happen is we're going to be connecting this battery to the steel wool.
Okay.
We're essentially building a
circuit. All right. When an electrical current moves across a circuit, what's actually happening is that the atoms in the circuit are being excited with energy. This causes their outer electrons to break away and move to the next atom. It's this reaction that lets electricity flow from the power company, through your house, and into your phone charger. But how is that going to light steel on fire?
Have you heard about the fire triangle?
Why don't you tell me about it?
Okay. So in order to create a fire, we need 3 things.
Okay.
We need heat, we need fuel, and we need oxygen. The battery is going to be our heat with the electricity.
Okay.
The steel wool is going to be our fuel.
Okay.
And the oxygen is just going to come from the air.
Mm-hmm.
Okay, first things first. Safety.
All right. All right, so should we just light her up?
Let's do it.
All right.
You want to do the countdown?
Yep, I'll count you in. All right, and 3, 2, 1, circuit. Oh, that's really cool. Wow. Ooh.
It smells really bad.
It smells terrible. Oh, wow. Oh, it's going. Oh, it's like a firework. It's like a little show down there.
This is really pretty.
That looks like a lot of...
Wow, like a lot of little sparks.
Yeah, they're just kind of doing their little spark life. And then they all sparked out. Wow.
Basically what happened here is that the current was just way too much for these really small, thin pieces of metal.
Mm-hmm.
And it just burned up. It couldn't handle it.
Oh, couldn't handle the heat.
It couldn't handle the electricity.
Here's the story. Metal conducts electricity. So when we touched the battery to the steel wool, its atoms started vibrating. But the battery actually added too much energy, making the steel wool's atoms so agitated, they vibrated around, creating a lot of heat. Steel wool's self-ignition temperature is 1,292 degrees Fahrenheit. So the heat generated by the atoms was enough to combust the steel wool and produce a flame. All right, do I get to do mine now?
Yeah.
All right.
1, go.
So I'm noticing there's just not as much burning.
It's because mine was more spread out, and due to the fire triangle, we had much more oxygen interacting with my steel wool.
I see. So there's little oxygen reacting with mine since it's all super condensed.
Pretty much just on the outside top part.
Yeah.
This is actually a really cool survival hack. So if you're ever lost in the wilderness, make sure that you have a battery and some steel wool.
Got it.
We're also gonna need some paper, but if you're in the wild, you can use some leaves.
Oh, All right.
So why don't you roll that up for me? And we're going to put it into the steel wool in the middle.
All right. Just kind of like.
So I'm going to be holding this.
Okay.
And you are going to put your battery.
All right. Fire triangle.
Fire triangle.
There it is. They're making their way around.
See if that's enough.
There's definitely heat being generated. Okay, there we go. There's fire right there.
And I want you to take a look at what you did. What exactly did you add onto this?
I added more oxygen to it. Okay, that's a really good flame.
Yeah.
I feel very proud about this.
Okay, if you thought that was cool, I haven't shown you the coolest thing yet.
Okay, I'm very intrigued.
And it has to do with our scale.
This scale right here?
Yes, this scale right here. So you might think, since we're burning, you know, something, that we would have a smaller weight afterwards.
Sure, because it burns and it kind of turns into a gas and it just goes away.
Right, but that's actually not what's happening here.
What?
I'm gonna prove it.
Okay, let's do it.
So here is some steel wool.
All right.
We've already pulled it apart.
Yep.
Let's put it on the scale.
Okay. It's 4.8. It's perfect. Okay.
4.8. Okay. You want to do the honors?
Oh, I would love to. You want to count me in here?
Yeah.
All right.
3, 2, 1, go.
I'm gonna do it a couple places. Oh, wow. Wow. It's going.
That looks like a nest burning.
Whoa. It's kind of hypnotizing.
Oh, and it's climbing.
Whoa,
The scale, oh my gosh.
Wow, it's
pretty
like
quickly.
moving.
Another 0.1, another 0.1.
So it's actually like pulling the oxygen then from the air and it ends up in our burnt product?
Yes. So we're adding mass.
Wow. It's now going even faster now.
Yeah.
All right, it's moving. Okay, there, it stopped. Okay, we're at 10 grams. It went from 4.8 grams to 10 grams, so it more than doubled.
Yeah, I told you, it's really cool.
That's impressive. Oxygen for the win. Kat, thank you so much for teaching me the fire triangle, but also showing me that you can actually light something on fire and it can gain in mass.
Yeah, you're welcome.
Now that Kat's got me thinking about energy, it's time to refuel myself. I have a pretzel stick and a donut. My two favorite treats. But which to eat? There's gotta be a way of knowing which snack will give me more energy. And you know, I might know the perfect person for the job. Hey, Alex.
Hello.
This is my good friend, Alex. She's a geneticist. And Alex, which one of these two would give me the most energy?
Well, we can figure that out if we figure out how many calories each one has. When we think of calories, we're thinking about food calories. Now, those are actually 1,000 lowercase calories with a little c. And that's what we're talking about when we talk about chemistry. We're talking about lowercase c calories, and that is the amount of energy it takes to raise the temperature of 1 gram of water 1 degree Celsius.
Wow. So like a full bowl of cereal, for example, is like, I don't know, 500 calories.
Exactly.
That would raise
the temperature of 1 gram of water 500,000 degrees Celsius.
Whoa.
Which is crazy.
It's a lot of energy.
It's a lot of energy. So we're gonna do a larger quantity of water and a smaller quantity of calories today using this.
And what is that?
This is a bomb calorimeter.
Did you say bomb?
I did say bomb. They've been used for hundreds of years to figure out how many calories, energy calories, are in something.
Okay, so what are we gonna be using today?
We're gonna light your choice of snack on fire.
How about the peanut?
The peanut is perfect.
Because there's a lot of calories in peanut butter.
Yes.
So I'm really interested to see how many calories is just in one peanut.
So what we will do is we will light that peanut on fire and we will see how much it raises the temperature of a certain quantity of water. We have 3 components here. Our large container, this is gonna be sort of our shell. A piece of cork here with a needle on it. We're gonna stick our peanut on that, so this is gonna be our little base. And what we'll do is we'll put this around our burning peanut, and then we will place a container with 200 milliliters of water on top of it. So as that peanut burns, it will heat up the water in this container, and we're gonna use our handy dandy thermometer to see just how much it raises the temperature.
Sweet.
Sound good?
Yeah, that sounds great.
All right.
So I need to put the peanut on the pin first.
Yes.
All right.
Don't stab yourself.
Wiggle it on there. Okay, I got it. That was pretty
Perfect.
good. Yeah, it was really easy.
I'm gonna fill our container here with some water.
Okay.
This is 200 milliliters of water, which is 200 grams of water.
Got it.
The first thing we need to do is get a baseline temperature of our water. So that looks like it is 24.6 degrees Celsius.
Okay.
So that's gonna be our starting temperature, and I'm gonna write that down so we don't forget it.
All right, so we have some data. Now, do I go ahead and light up the peanut?
Yep, you are gonna light that peanut on fire.
Okay, here we go.
It's got some good fats in there, which should help it light. No, you're charring it for good.
Okay, well, I do have another flame if this is not gonna work. Yep, that's not gonna work.
Nope.
I've got a... Okay, it's on fire.
That's good. All right, so now the peanut is on fire, and we put this on top, and we're gonna let that peanut burn, and we're gonna watch the temperature of this water go up.
It's already going up.
It is already going up.
I am really impressed how well that works.
Yeah, it's a really cool system.
Using the bomb calorimeter only gives a measurement of the peanut's potential caloric energy, not the amount we can actually ingest. That's because the fire burns the peanut much more efficiently than my gut can digest it.
The way that we actually figure out the number of calories in food now is not by sticking every candy bar into a bomb calorimeter. We can use something called the Atwater system to do this. And what Atwater did is he looked at the different components of fat, carb, and protein and figured out generally for each of those how many calories a certain number of grams would give off.
Essentially what it does is it makes it more useful for humans.
Yes.
Because, for example, I cannot eat a log of wood, but a log of wood would burn really well.
Exactly. So it takes into consideration that your metabolism doesn't work just like fire.
Got it.
So I think our peanut has burned out now. So it is now holding at the end temperature of 33.1 degrees Celsius. So we can take our bomb calorimeter apart, give that a little squeeze and see how much of that peanut is left.
Oh my gosh, nothing. It's just ash.
Yeah, so we burned up most of the usable energy in that peanut. It all went into our water.
Wow, that's kind of like just charcoal.
Yeah, it's almost all of the usable energy is gone from that peanut.
Wow.
So now what we can do is we can use our two measurements to
Okay.
figure out how many calories were in that peanut.
So we have two different numbers. We have the 24.6 and 33.1. So our peanut raised the temperature of our water by 8.5 degrees Celsius. Using Atwater's calculation, that means this peanut has 1,700 calories of energy. Or, if you're reading a nutrition label, 1.7 uppercase calories per nut.
And you can imagine you could do this for any of the foods here on the table and figure out which one was the most energy dense.
If you guessed the donut, you'd be right. Because of its high fat and sugar content, it packs a punch. A donut has caloric energy equivalent to a stick of dynamite. Of course, dynamite explodes all at once, while a donut's energy is used gradually after the initial sugar rush. Alex, thank you so much for showing me how you can calculate calories with some really simple items.
You are very welcome.
And now it's time for some simple science with my engineering friend, Maynard.
If you're in love with rockets, then this next experiment might be right up your alley. Fire and heat have been used to generate movement for centuries, but you don't have to be an expert in combustion to get motion from a little fire. You can capture the magic right at home with just two common objects. Hopefully you're in the mood for a cup of tea, because the first thing you're going to need is a tea bag. First thing we want to do is cut the top of the tea bag off, the part that contains the staple and the string, just like so. Now, you want to empty out the contents of our tea. We should now have a column that looks just like this. Stand the tea bag up on the table. When we light the top of the tea bag, like we're going to do in a second, the fire will burn from the top to the bottom, creating a hot column of air that's trapped inside the rocket. This increase in temperature causes the air to become less dense and creates a low-pressure system. The less dense air now rises above the cooler air around it, creating lift that takes our tea bag along with it. Watch this. Wait for it. How awesome is that? This pressure shift is known as a convection current. It's the same principle that makes hot air balloons take flight. Just like in our tea bag, hot air balloons use heat to create a pocket of hotter, less dense air. This expanded air inside the balloon is what creates lift to help carry the balloon off the ground. Now, of course, when it comes to the remaining ashes in our tea bag, what goes up must come down. So make sure they come down somewhere safe. And that's just one simple way science keeps things moving.
I've been pretty impressed with our sources of fire so far. I mean, who knew a nut would burn like that? But my chemist friend Cole says he can make the seemingly impossible happen. Get liquid water to ignite some flames. I say, game on.
Hey, Nick.
What's up, Cole? This is my friend Cole. He is a chemistry guru. Okay, Cole, what do you have for us today?
We're going to be taking a look at what happens to sodium metal when it is exposed to water.
Sodium is one of the most common metals used in a variety of industries, from metalworking to food processing. We use it to make table salt, baking soda, and believe it or not, titanium. Sodium is an alkali metal. This means on an acid to base scale, it rests firmly at the base end, with a pH of 14. Alkali metals are incredibly unstable. When an element is unstable, this means its atoms have an unequal number of positive and negative ions. By nature, atoms hate being unstable and will try to make connections with any material around them in order to stabilize. That's why in nature, sodium is always part of a compound, like table salt. So why is it never found alone? It has to do with water.
Sodium on its own has a pretty toxic relationship with water. Water is in basically everything because water is in the air. It's in the air we breathe in, it's even more in the air that we breathe out.
So this is not sitting in water, because it looks like water.
Correct. That is actually mineral oil, and it's there specifically to prevent it from coming in contact with water. When sodium comes in contact with water just in the air, it undergoes an oxidization process that kind of helps it decompose. When it interacts with water the way we're going to see here in a second, it does something a bit more interesting.
Okay, so what's the first step?
Well, the first step is that we're going to go ahead and take out some of this sodium here. And I'm just going to take one of these tiny sodium blocks. And sodium is kind of an interesting metal because it's really squishy.
Sodium's softness comes from its atomic structure. The atoms making up this element are large and their bonds are weak. Think of it like a sponge. There's lots of empty space in sodium, which means you can cut through it even with a dull knife. And once our piece is separated, it's time to see what happens when we put it directly in water. All right, we're gonna go ahead and put these on. I'm gonna move this back too, geez.
Thank you.
Save the good stuff.
All right, you ready?
All right, in 3, 2, 1, sodium. It's sparking. Oh, it's on fire. Yeah. Oh, wow.
Come on.
Oh! You literally created a firework with sodium and water. A toxic relationship for sure. They should not hang out, ever.
Yes.
At all.
Amen.
Wow, it's kind of like all over the table now. Okay.
Yeah, a bit of our messier reactions.
Cole, what just happened here?
So in order for fire to occur, you have to have that fire triangle, which means you need access to oxygen, some kind of heat, and some kind of fuel. In this case, the heat is being provided by the exothermic reaction, basically sodium breaking down on the atomic level when it comes into contact with water. The oxygen is being provided by oxygen. But then the other thing that's happening is the sodium is essentially acting as the fuel because it's part of that exothermic reaction.
Got it. And it's also producing hydrogen, correct?
Yes, exactly, which is still burning in that reaction. It's one of the things that's responsible for the big pop, is the buildup of hydrogen gas.
Oh, wow.
Yeah.
Jeez. So we put it in there, and it's kind of skipping around a bit. It explodes.
Exactly.
That catches the hydrogen on fire.
Yep.
It also catches the sodium on fire, which burns this really cool kind of orangish red color.
Yep.
And then we have basically a fireworks show of science.
Exactly.
I love sodium, and I love when sodium and water hang out, even though they shouldn't.
I like it on my fries, but I gotta say, I think I like it a little bit more when it catches fire.
I love it. Thank you, Cole. Sometimes science is too large for the lab. For our next demo, we've got to get outside. All right, so this is rocket candy. But this is not candy NASA astronauts eat, nor should anyone else. It's a nickname for a fuel source used by rocket enthusiasts on Earth. I've already created a small batch, and today we're gonna see how it works. The main ingredient in here is sugar, and sugar makes a really great fuel because it's a combination of glucose and fructose. And all living things on the planet use glucose and fructose as a fuel source. However, if you just light sugar on fire or try to, it kind of turns into like a pool of caramelized sugar. It smells really good, but it's definitely not rocket fuel. To make sugar into rocket fuel, we need to add oxygen. And the way that we're gonna get that is the oxidizing agent, potassium nitrate. Potassium nitrate is a really versatile chemical. It's been used since the mid-1920s as a food preservative in meats because it adds a nice salty flavor and pale pink color while hindering bacterial growth. Potassium nitrate is also the main component in gunpowder, a core ingredient in fireworks, and has been added to toothpaste to reduce sensitivity in teeth. That's right, you've been brushing your teeth with firework powder. Sugar is our fuel, potassium nitrate is our oxygen source. So what would happen if we added a little bit of heat? Let's find out. So we're making rocket fuel, so I feel like I should definitely suit up for safety here. So I'm gonna go ahead and put this face shield on, gloves. So we're gonna add a little bit of heat. All right, let's see what happens. I'm gonna go ahead and wait for that wind to stop. All right, and here we go. I'm gonna light this wick. I'm gonna light this wick. Oh boy. Oh my God! Okay, that was really intense. That was basically it was like a firework in this little dish here. Lots of combustion, lots of fuel, lots of fire. The reason that it didn't actually go anywhere is because it's actually kind of like a rocket upside down. So the force is actually pushing into the table. Otherwise, I'm pretty sure if that thing were this way, it would have actually taken off up into the air. This reaction actually burns right around 2,000 degrees Fahrenheit. And we can definitely see that by the fact that this melted to the tablecloth. So this got extremely hot. And so there's only one way to go from here, and that is up. And so that is to actually have a bigger piece and light that on fire. So let's do it again. Oh God, the suspense. Oh, it's going. Oh my God! The table is on fire. Okay, we want that to put that out. I got some water right here. All right, gonna go ahead and just slowly put some of this. Okay, there we go. That is incredibly hot. This reaction gets up to 2,000 degrees Fahrenheit. I believe it. That was an absolutely insane reaction. Definitely oddly satisfying. I'm Nick Uhas. This is Oddly Satisfying Science. We'll see you on the next one.